Hello, welcome to Petrochronics, a research group and extension project focused on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTT Talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello everybody, good morning. Welcome to our PTT talk. Today we are going to talk with Chris Yakymchuk, and we are the team who will be hosting his talk with him. And today we have a big team. So I'm Catarina da Paz, a PhD student at the University of Waterloo, and I'm here with Maira Tedeschi, a researcher at the Geological Survey of Finland, Ciro Lacerda, a professor at the Federal University of the Jequitinhonha and Mucuri Valleys, Rafael Mota, a professor at the Federal University of Rio Grande do Norte, and Lucas Tesser, a PhD student at the University of São Paulo. So thank you, Chris. It's a pleasure to have you here with us.
Thank you so much for the invitation. It's wonderful to be here, and I am ready to go whenever you are.
Thank you, Chris. It's really great. We will just do some introduction for you and for the talk. I will start with introducing a bit Petrochronics. So we are a community integrating people who enjoy working with petrochronology and geodynamics, and we have a series of actions to put this community together. And Ciro will talk a bit about the PTT talk.
Hello everyone. So the PTT talk is a series of talk discussions that we receive some researchers around the world to talk about geodynamics, petrochronology, and associated topics. So if you are interested in these topics, following us in our social medias and share this link, share this video with a friend, and that's it.
Good morning, everyone. I'm very excited for today's talk. We have the pleasure to listen to Chris Yakymchuk, who no needs introduction, but this is basically my job here today. So Chris is an associate professor at University of Waterloo in Canada and leads research focused on the behavior of accessory minerals during metamorphic process, aiming to reconstruct the tectonic framework and the geodynamic evolution of orogenic belts of all ages. Thank you and welcome, Chris. Now I'm gonna pass the word to Lucas, who's gonna introduce the topic of the presentation. It's up to you, Lucas.
Hello, everyone. Firstly, I would like to thank you, Chris, for your precious time here with us, and also Katarina for inviting me to introduce Chris Talk. It's a pleasure for me. Well, when we think about metamorphic rocks, we usually think on the rock form minerals, right? Such as garnet, feldspars, pyroxene, biotite, and so on. But in fact, are the tiny accessory minerals that will play a crucial role in controlling the most important trace elements in the rock. For example, if tiny amounts of zircon or monazite grows during metamorphosis, they will govern on where those elements will go, if they will stay in the residue or if they will move into the melt phase, for example. So despite they being called as accessory minerals, they often play a more important role in this metamorphic game. Sorry. And one of the really exciting recent advancing in the recent years has been coupling thermodynamic modeling with mineral melt trace element partitioning. And here is exactly where Chris has made some major contributions. His recent works has helped many of us to rethink some assumptions in petrology, for example, in using classical geochemical proxies to infer magma depth generation and how we interpret zircon stability during the first steps of partial melting and a lot of many other examples. So because of all of this, I consider that today's Chris talk is pertinent to everyone, not only interested in metamorphism in general, but also in people that are interested on better understanding how we can interpret complex petrochronological data sets of accessory minerals in metamorphic rocks. So Chris, I'm looking forward for understanding better how accessory minerals evolve through the lens of phase equilibrium modeling. I wish you an excellent talk and obrigado.
Yeah, so Chris, I'll put your presentation here, and whenever you feel it to start, you can.
That sounds good. Just put it up on the screen. Thank you, Lucas. That was way too nice, by the way. Obrigado. All right. I think it's live. I think it's working. Okay, fantastic. So I'll take over from here. Thank you again to the Petrochronics community, Katarina in particular, for inviting me and helping me get this all rolling. So it's a pleasure to be here. Today I'll be talking about accessory minerals and trace element modeling, and it'll be kind of a high-level investigation, a little overview of what we've been doing the last kind of decade or so, trying to understand accessory minerals and linking the trace elements of those to bigger processes using kind of numerical approaches. And so I've summarized this on this little image here. The best record we have of rocks and minerals and metamorphic processes is the rock record, which is what this little laptop's sitting on here. But sometimes we kind of get overwhelmed with large data sets. And so we need ways to kind of think about what are they telling us about real processes. And that's where I think numerical modeling kind of comes in. And this can be in the form of phase equilibrium modeling of very, very detailed thermodynamic things. But it can also just be mass balance and trying to think about things from kind of a fundamental perspective. What are the processes that occur in metamorphic and igneous systems? And how can we use the kind of the natural rock record to understand those processes? So the modeling never solves anything, but it gets us to think deeper about some of the processes that occur in natural systems. And so right here, I also put a picture of what I like to call a binary zircon. It's just a bunch of zeros and ones that kind of make up this image. So I'll be talking today mostly about fake rocks. These are just zeros and ones in the background of a computer. But again, it's not about understanding fake rocks. It's about using these fake rocks and numerical codes and whatnot to give us things to think about with the natural rock record. So I'm going to emphasize, we don't make big insights from modeling. We make it from looking at the real rock record and real data that's really hard to collect sometimes, and thinking deeper about the processes at play using the results of modeling. And so before I continue on in this presentation, I'm going to do a very, very short call out to a conference that I'm organizing next year called Granulites and Granulites 2027. More details will be coming on all the listservs shortly, but in the meantime, those are the dates there. It's going to be a fun time kind of north of Montreal in Canada, looking at some high temperature metamorphic rocks. So let's get going into the talk. So why accessory minerals? Well, here's kind of the reasons we should think about accessory minerals in metamorphic and igneous systems. They're usually the best chronometers. We use them to put a little t, to the pressure and temperature evolution. And many are stable over a wide range of pressures and temperatures. Zircon can be one of those that you can find at relatively low metamorphic grades, high grades, low pressures, high pressures, you name it. Some can be modeled using phase equilibrium tools, and I'll explore that in a little bit more detail in this talk. Some can be partially and completely modeled, and some we just kind of use the modeling to give us a sense of how might they behave. We don't really know. Why are they important? And Lucas kind of talked about this, is that they may be a very small proportion of the rocks themselves, but they have a disproportionately high amount of a lot of trace elements. They're also key controllers on isotope ratios, things that a lot of geochemists have used for decades. Cerium, neodymium, rubidium, strontium, even hafnium isotopes. These are things that are kind of tied to the behavior of accessory minerals. And so we have to understand how they behave in order to interrogate the isotopic data appropriately. And finally, some play important roles in buffering component activities. And the one I'll talk about in a little bit more detail later is titania or titanium activity in the context of understanding temperatures in metamorphic and igneous systems. So here are just a few images. A cathedral-luminescent image of zircon, nice zoning. Here's a yttria map of some monazite crystals. Here's a nice blue apatite crystal from the field. And I didn't have a good image of allanite because it always seems to be breaking apart on me under thin section from metamictization. So I just put a picture of weird Al Yankovic just for the comedy aspect of this talk. So that's why accessory minerals. So how do we think about these in terms of numerically? How do we model them? And so what I like to take is called a layered approach. And I didn't start this. I'll talk about where a lot of this comes from, but I'll just give you an overview with this little diagram here. What we usually do is think about what are the controlling factors, especially in rocks that have a little bit of melt in them. They're just easier to kind of model in these systems. So if we look at zircon solubility, for example, this is kind of an expression, experimentally derived, of how we expect zircon to behave when there's melt around in the system. And the key things that determine whether zircon is going to dissolve or grow or just stay as it is temperature. This kind of value here, M. And this is basically a ratio of various components in the melt. And this can be tied to experimental contributions. So the only two things based on this expression that seem to really influence zircon behavior in high temperature metamorphic rocks and igneous systems is temperature and the composition of the melt. There are other formulations that look at other compositions of the melt or even pressure, but the dominant one is temperature and melt composition. So what we do is we take that from the experimental literature and say, okay, those are two things that we can actually model with phase equilibrium modeling. We can model temperatures. We can model the compositions of melt. And so we start with some kind of underlying thermodynamically constrained model of rocks and minerals, and important for us right here, melt. And we take that as a function of, say, pressure and temperature, and we take out the things that are of interest for, say, zircon. We can do the same thing for other accessory minerals, but we'll start with zircon, where we take out basically the melt proportion, the melt composition, and built into this below is temperature as well. And we basically take all these things out in kind of layers, And these layers are kind of combined together with additional calculations along the way to come up with some indication of how we expect that accessory mineral to behave. And I'll talk a lot more about this as we go. And it's all anchored to kind of our underlying thermodynamic model, something that you can learn a lot more about by reading the literature and looking at short courses and whatnot. I'm going to assume that we have a working understanding of this thermodynamic modeling where you put in a bulk composition and you see what the thermodynamics predict should exist as a function of that composition, pressure, and temperature. And what we're going to try and do with this talk is kind of dig through that deeper and what are the outputs of those models that we can then layer into an accessory mineral modeling behavior. So there's a lot of limitations of this approach, and I'll talk about these as we go through today. But some of them include not considering trace element substitution in major minerals. That's been changed recently, but that's an indication of something that's a bit problematic what we do. It relies on extrapolation of these solubility expressions to kind of extreme pressure temperature conditions outside of which they've been calibrated for experimentally. Experiments are usually done at higher temperatures just because of kinetic things, and so we have to kind of extrapolate those down temperature. And finally, they are anchored to the experimental data and the predictions of phase equilibrium modeling. That's why I put that little image of an anchor. If there's an issue with those underlying models, well, that's going to propagate all the way through this system towards the top. So be aware of all those uncertainties and limitations, which is why I'm very cautious of applying these to an individual real rock, but looking at this from how do we expect real rocks to generally behave and what can it point us in the right direction for interpreting our accessory minerals. So to do this phase equilibrium modeling, there's a few ways to do it. It's basically, there's two general ways to do things. You can basically do it with software such as ThermoCalc, which is extracting data manually through it, which can be kind of a pain. Melts can do this as well, rhyolite melts in particular. There's other kinds of software we can use to provide gridded data that we can then use to take out pressures, temperatures, melt compositions, and so on. And I'm becoming a very big user of this new one called MageMin, which can do accessory mineral calculations as part of the underlying phase equilibrium modeling. As long as you know how it's being done, you can have some faith in it. But I would be cautious of just turning this button on without thinking about it in a little bit more detail. But I would really like to compliment Nicholas Riel for this work on MageMin, and it can do these accessory mineral calculations in it as well. So lots of ways we can do this for various bulk compositions. And so let's take an idea of we have these modeling outputs, we have temperatures, we have melt compositions, and so on. And let's start thinking about how we expect accessory minerals to behave in these contexts. So the main thing we want to think about with accessory minerals is they have building blocks, just like major minerals, okay? Most major minerals are built up of silicon, aluminum, iron, magnesium, calcium, and so on. So we have to use that same mindset to think about the accessory minerals. So if we think about the mineral zircon, for example, these are the main building blocks: zirconium, silicon, and oxygen. Monazite, we have light rare earth elements and phosphorus, so that's a phosphate mineral. Apatite, we also have phosphate as part of it, so phosphorus as well as calcium. So you can see if you understand the essential structural constituents or the building blocks of these, then you can kind of integrate them into the modeling. Now, what I haven't done here yet is talked about the other trace elements that goes into these, the ones that Lucas talked about. They're kind of the important ones that kind of go disproportionately in the accessory minerals. I'll talk about that a little bit later. But the key thing is understand your building blocks. And when you look at the building blocks, we look at things like zircon, which has zirconium as one of the key cations that makes up zircon. And you have to ask yourself, okay, if zirconium's around, what other minerals and phases are key repositories for that zirconium? And if we look at certain minerals that we commonly see in metamorphic and igneous rocks, so feldspar doesn't really contain a lot of zirconium, but garnet does. It can contain hundreds of ppm of zirconium, which means if there's a lot of garnet in your rock, well, that's going to play with the zirconium budget, which will have a downstream influence on how much zircon and the behavior of zircon in these rocks. So the typical reservoirs of zirconium in a lot of metamorphic and igneous systems are zircon and melt. But we can't get away from the fact that sometimes things like garnet can also contain an appreciable amount of the budget of that. So I just want to put that in your minds that we have these building blocks. And yes, we usually think about them going into the accessory minerals and to the melt, but once in a while, they can also go into the major minerals. I'll explore that with a few accessory minerals as we go, but I want to put that in your heads as something we'll consider moving forward. So some accessory minerals, namely zircon, there's been attempts to calibrate their underlying kind of thermodynamic parameters. So here, basically, we have zircon, and I've divided up into monazite and apatite here. So the thermodynamics and the kind of end members of, say, the molar volume, the heat capacity, enthalpy, entropy, and so on, these are fairly well constrained for zircon. perhaps we can do better, but they have a good background, and you can see some of the details are in this paper here, which means we can integrate them kind of directly into phase equilibrium modeling. That's great. But there are other minerals that are a bit more complicated, especially those that exhibit solid solution with other things. So monazite and apatite, we don't really have a great sense of the underlying thermodynamic parameters. There's been some progress on this, and this is a table from Frank Spear and Joe Pyle's work, just showing how we have apatite as a couple end members, hydroxyl apatite, and a cerium end member, and the various thermodynamic properties that go into that. And you can see that there are numbers there. I would argue that these are a good starting point. We need a lot more work before we can directly put these into thermodynamic models. But there is some motion to be doing that even right now with some more advanced techniques as well. So the key aspect of this is we have to think about how these particular minerals and their essential structural constituents or building blocks go into, say, zircon versus melt. But also when there's other major minerals around, we have to worry about that. So right now, for example, we don't have a very good idea of a zirconium end member of garnet. Why? Because that doesn't naturally exist. So what we need to do is kind of use some mathematical magic in the background to come up with an approximate end member properties of zirconium garnet. And these are things that people are working on right now, and I hope to see some results in the next few years for this. But in the meantime, we usually use this layered approach where we're looking indirectly at zircon rather than building it right into the thermodynamic modeling. So if we take our approaches of, say, accessory mineral solubility from the experimental work, or this direct approach that I alluded to in the last slide, here's just an example from Dave Kelsey's work from the early 2010s, just showing what we expect zircon to do. So here we have a PT, or pressure temperature phase equilibrium diagram, also known as a pseudosection, and lots of other synonyms for these things. Pressure as we go up, and temperature as we go towards the right. So increasing temperature up, increasing temperature towards the right. You'll see here we're starting these diagrams about 650 degrees. So we're looking at rocks that are pretty high temperature and have started to melt. And the amount of melt as a function of pressure and temperature are shown by these contours here, 5, 10, 20, 30, and so on. And for those of you unfamiliar with these diagrams, what's happening in the background is we have these shaded panels. It's kind of like a stained glass window, and each panel represents a stable phase assemblage. And you can see them labeled as such. The V is for the variance based on that system. But as we go from one panel to the next, we either gain or lose a phase. And that phase can be a mineral, it can be a fluid, or in this case, it could be melt as well. So I won't go into more detail about explaining phase equilibrium diagrams like this, but be aware that as we go from one shaded panel to the next, we're looking at the addition or removal of a phase from that stable phase assemblage. And so what you can see is here, as the amount of silicate melt increases, we can then move to the diagram on the right, and it shows the zircon mode, basically the amount of zircon predicted to be in the rock as a function of pressure and temperature. And it's quite strongly tied to melt composition, which is why these are paired diagrams. But as we increase temperature, you can see these numbers, they're pretty small because the amount of zircon in any rock is pretty small. But you can see how it's decreasing. 25 times 10 to the negative 5, and it's going down to 20, 15, 10, 5, up until this little dashed line where all these zircon is expected to be exhausted at that point. And the idea here is that the amount of melt increases in the rock as we move from left to right. The amount of melt is increasing, and that wants to take in more and more zirconium, because zirconium solubility in the melt is a function of temperature, melt composition, and that's fine. But also, in terms of the whole budget of the zirconium of the rock, the more melt we have in the rock in general, which is alluded to on the left, the more zirconium is needed to fill up that melt with zirconium to make it happy, for lack of a better word. And so what this tells us is as we increase temperature, zircon is dissolving. In other words, in a suprasolidus or melt-present metamorphic system, if we decrease temperature, zircon is expected to grow. And so this leads to the kind of the hypothesis that most zircon in high-temperature metamorphic rocks is not growing during the heating phase, but during the cooling phase. And this was kind of proposed by Dave and others at the time. And there's been a lot of modeling that has replicated this using different approaches. But there are some things in the literature that say, well, maybe not all the time. And I'll come back to that in a little bit. So if we think about another mineral such as monazite, and here we have a pressure temperature diagram that extends to even lower temperatures. And you can see here we have the composition of monazites on the right, and the amount of monazite, the moles of monazite right here, is shown in these blue contours. And the key thing to look at is as we increase temperature, even in the subsolidus realm, and where my laser is going now, it's into the supersolidus realm, as we are increasing basically temperature, we can see here the amount of monazite is increasing. It's going from 0.44, 0.45, 0.46, and so on, millimoles. But once we hit that solidus, or that partial melting, we actually see that amount decrease pretty quickly. And what this indicates once as well is during prograde metamorphism, we're probably growing monazite, which kind of represents a lot of the monazite we see in the microstructures we see with monazite. But once we're above the solidus, monazite's expected to be consumed, similar to what zircon is. And again, this is something that the modeling from various approaches is showing, but the real rock record doesn't always show this. But it's telling us in general something to think about. As the amount of melt increases, why would monazite stick around if that melt wants to take in the building blocks of monazite? It wants to take in the phosphorus, wants to take in the calcium, and so on. And so here's just a series of diagrams illustrating this point a little bit further, that both the amount of melt and the composition of that melt changes as a function of pressure and temperature. So same again, we have pressure going up and temperature going towards the right. This is just an example for an average metapelite. And what I've plotted here are the various proportions of melt, which is the top left, the mole percent of melt in the system. Again, as we increase temperature, the amount of melt's increasing. This is kind of intuitive. Heat it up, rock melts more. But you can see there's a few variables I've contoured here that are relative to, say, zircon and apatite and monazite solubility. You can see here, melt to the aluminum saturation index generally increases. And what that means is that the kind of luminosity of the melt is expected to increase as we increase temperature in these rocks. And the luminosity of melt is actually quite highly tied to apatite solubility. More luminous melt can dissolve more and more apatite to hold more and more phosphorus. You can look at things like silicon, which can also impact things like zircon solubility. And we can look at the amount of water in that melt. And the key thing about the amount of water, dissolved H2O in that melt, is that things like phosphate minerals, in particular monazite, can be quite sensitive to the water content of that melt as well. But the key thing I just want to point out here is that the melt compositions, in this case for an average metapelite, but you can do the same thing for melting other rock types, or even looking at granites and how they change during crystallization, these variables can change. The one that kind of drives accessory mineral behavior the most, I think, is just the proportion of that melt. We want to try and fill that up in an equilibrium system with, say, phosphorus and zirconium. But there are other factors, including melt luminosity, water content, that can also impact that, the solubility of accessory minerals. Or in other words, if we expect these accessory minerals to be stable, to grow, or to break down. So that was kind of looking at the results of kind of a melt composition. What we can also do is think about accessory minerals, and this is an example of zircon, but from a mass balance approach. This is a paper from Matt Cohn and others from 10 years ago. And I think it was quite good because what it showed is we can think about the different reservoirs of zirconium, which is a building block of zircon, in basically the different minerals. And there's a table up on the right just showing, based on compiling the literature and some individual analyses, what the zirconium contents of different minerals are. And some of these are pretty low. You don't have to worry about how much plagioclase is in your rock for zircon solubility because it doesn't have much zirconium, 0.09 ppm, for example. But there are some minerals, and here's an example of garnet, and it's on a log scale, and it's on an inverse temperature plot here, but it shows that as we increase temperature, the amount of zirconium, which you can track on the right-hand side here, strongly increases in garnet in general. And so Matt and the team put together kind of an expression for that. And what they did is they went through this exercise looking at, okay, if we have this much zirconium going into garnet, and this much going into hornblende, this much going into the melt, how much is left over to actually make stoichiometric zircon? So I call this a mass balance approach. And it shows eerily similar things to what we were seeing from Dave Kelsey's style model of monazite and zircon solubility. And so how this kind of modeling works in theory, and this is a lot of text on the slide, so you can go back to the video and go through it. I'll just quickly go through it. But we basically have to start with a rock. We melt it. We do this underlying phase equilibrium modeling. The most important question is how much melt is in the system. So we go with that. And then we calculate the amount of melt, the composition of that melt. We layer it in with these solubility expressions and eventually come out with, well, how much zircon just by balance is left in that system? How much monazite or apatite just by balance is left in that system? And so that's kind of a walkthrough briefly of how it works. I won't read it word for word, but I want to focus here on the caveats and some of the assumptions. And I think these are the things that when we did this modeling originally, and when Dave did it as well, and Matt and team, all of these groups were doing this, is we have to think about all these caveats. And I think these explain some of the disconnects between sometimes what we see from modeling and what we see from the real world. So we assume with this approach shown here that all the zirconium for zircon, light rare earth elements for monazite are basically between melt and those accessory minerals. And I just showed you a slide. That's not necessarily true. We assume that the grains of monazite zircon are not sequestered as inclusions in other minerals? In other words, are these minerals, accessory minerals, actually reactive? We treat this as an equilibrium system. Everything's communicating all the time. Everything's talking. What if it's not? And I think that there are cases where that's clearly they're not communicating. And we don't consider implicitly in these models the kinetic effects of dissolution. Why? Because these are equilibrium models. They're assuming there's no kinetic hindrances, that everything is talking and happy, and there's no time lag in these processes. But in the real world, there probably is. So here's an example, just coming back to kind of Matt Cohn's kind of the mass balance approach. And what it showed here was that here's a PT path for a metabasite. A different rock type now, not a metapelite, but a metamorphosmafic rock. And the idea here is that these different PT paths show gray areas and red areas. And the gray areas, based on mass balance in the PT path, usually the heating, this is where we don't expect zircon to grow. We expect it to dissolve. Why? Because zirconium-rich minerals, garnet, to a lesser extent hornblende, these are increasing in their proportions as we increase the temperature. And if they're increasing in their proportions, well, they're not releasing zirconium. If anything, they want more, right? So it's a simplification, but it's a mass balance approach, and it shows that these red areas is where zircon's expected to grow during cooling, both at subsolidus conditions and supersolidus, based on just thinking about what is the zirconium budget, or how much is in garnet, how much is hornblende, how much is in melt if melt is present, and how much is left behind to make zircon. So this is what the modeling seems to be telling us. And then what I did a few years ago is I thought, well, one of the issues we have is that zircon does seem to grow sometimes during heating, especially above the solidus. Now, I don't think there's a lot of cases of this, but I think there are some that are hard to refute. And so what I tried to do is combine Matt's approach of the kind of the bulk mass balance approach with Dave Kelsey's solubility approach into something else. And so what I have here are pressure temperature diagrams. There's underlined pseudosections. I just removed those kind of colored panels just to make it simpler. What we have is what's called a distribution coefficient for the bulk distribution coefficient for zirconium, essentially telling us if we look at all the phases in the rock, melt, zircon, garnet, hornblende for the mid-ocean ridge basalt on the right-hand side, how much zirconium is expected to go into the melt versus the solid residue as a whole. And we use that to say, is zirconium compatible or incompatible? Anything below a value of 1, zirconium is generally incompatible. And I think that's pretty acceptable. Zirconium does like to go into the anatectic melt. You can see in these two. But the key thing that I tried to approach was, is the zirconium very incompatible or just a little bit? What you can see here is the farther you get from 1, the more incompatible zirconium is. And the closer you get to 1, the more compatible zirconium is. And the key thing is when we look at all the phases in the rock, this value changes. And so I'm asking the question, how incompatible is zircon? It's a little bit different for the morb. Okay, there seems to be an increase in incompatibility as we increase temperature, but it seems to be the opposite for the metapelite. And so we're going to take that aside, and I'm going to come back to the kind of key conclusions from this, which is, can we grow prograde zircon, which is heating, which is increasing temperature, keeping in mind all of these mass balance constraints? Can we grow zircon at high temperatures above the solidus during heating? And when you do this mass balance approach, when you consider the relative amounts of incompatibility, the answer is yes, you can. A little bit, right? And so here we have a series of plots. These are called mode box diagrams. What they're showing at a fixed pressure, 6 kilobars in this case, increasing temperature from, say, 650 below the solidus up to above 700, all the way up to 950 and so on. You can see the amount of the different solid phases in the rock. So, not just solid, we have liquid as well. But as the temperature increases, the liquid increases. And if we think about, well, okay, we have that amount of liquid increasing. How much zirconium as a function of the total amount goes into the liquid? You can see here, it's about half of it to a little bit more. Garnet contains a bunch of zirconium. Plagioclase a little bit. It's an artifact of the modeling. We couldn't find a good distribution coefficient for plagioclase, but there we are. Biotite goes away, and the amount of zirconium in ilmenite is actually quite high. So if we remove melt from this particular one, and we just renormalize this for just the solid minerals, in other words, what other than zircon is expected to take in zirconium, you can see the key players are garnet and ilmenite. So as we increase temperature, the amount of zirconium in ilmenite decreases, but the amount in garnet increases. That's all fine. But if you look at this diagram, in the first kind of 50 degrees or so, you can see there's this little dip in the amount of garnet there, okay? And there's also a little decrease in the amount of ilmenite there. And this is an area right above the wet solidus where there are some interesting reactions that are expected to occur in a metapelite, where we are actually breaking down a little bit of garnet and a little bit of ilmenite. And right above the solidus, where we do this, we actually overwhelm the melt with the amount of zirconium that's released in this, and we can create a little bit of zircon right above the solidus. And if garnet grows after that, that garnet can shield that zircon from further dissolution later. So this was kind of combining a couple different types of modeling together to show we can sometimes do things that the general modeling doesn't expect, which is we can grow a little bit of zircon above the solidus during heating if we're considering the distribution of zirconium in these different minerals. So that's just an application of kind of combining some of these different modeling approaches together, which I think is kind of fun. Here's a single slide just showing another little approach of this, which is one of the key kind of observations from rhyolites, so these are igneous rocks now, is that a lot of the zircon have high titanium rims. And titanium is usually used as a proxy for temperature. And how this is interpreted by a lot of the volcanic community is that we have this kind of magma chamber, and the zircon crystallizes and so on, and then we bring in a new pulse of hotter liquid or hotter magma, which causes zircon to grow again, which gives you a higher temperature, apparently higher temperature rim over a lower temperature rim. And so a group of us did some work trying to look at this. Well, what's an alternative? Well, how about we just basically bring a silicate liquid up towards the surface of the Earth, and we allow it to adiabatically ascend. Can we just produce apparently high temperature rims on zircon without magma recharge? And without going to the details of this plot, yes, you can. You don't need magma recharge. It's not the only explanation for high titanium rims on rhyolitic zircon. And what this is showing is as we just take a silicate liquid and we bring it towards the surface adiabatically, so fast ascent, all right, we can actually increase the apparent concentration of titanium in the rims of the zircon that's growing. So essentially, I don't think this explains all rhyolite systems, or maybe not even most of them, but it's an alternative that the modeling was pointing us in a direction of to magma recharge and understanding the systematics of rhyolites and high silicic volcanic rocks, which I just think is kind of neat. There we go. One other thing that some of us played with a while ago was trying to think about phosphorus. And the problem before that I mentioned is that we have apatite and monazite. Both are phosphates, which means they're going to be competing with each other for phosphorus. And there's some ongoing work on this right now. But the other thing is the key building block of monazite are the light rare earth elements. But if you measure apatite, they can contain appreciable amounts of light rare earth elements too. And the amount of apatite in any given metamorphic or igneous rock is usually a lot higher than if there's any monazite there. And so this is just a pressure temperature diagram showing the amount of monazite dissolution as a function of temperature and pressure. So kind of mimicking what we saw earlier with zircon is as we increase temperature, the amount of monazite is being, in this case, we have inverse kind of contours where the amount of monazite is being dissolved increases. And after 100%, all the monazite's gone. Now, if we actually do a combined model during mass balance, where we say, well, let's allow some of the light rare earth elements to go into the apatite, because that's what apatite does in the real world. And what it effectively does is when we allow light rare earth elements to go into multiple minerals, including apatite, we can actually create a situation where monazite's expected to be completely dissolved a little bit earlier. Now, I'll admit that this was some pretty rudimentary modeling that I tried, and there's a group of people working now on a more quantitative, using fancy algebra and so on to do this properly. But as a first pass, it makes us think, well, when we're thinking about monazite or apatite, what are the building blocks? And does the building block of one substitute into the other? And what does it do for that one? So there's this kind of iterative kind of almost battle between certain accessory minerals for these essential structural constituents. So main thing that this study showed, I think, is it's worth considering sometimes. I'm not trying to solve the world with these studies, but start to think about phosphorus and the different players in the realm of phosphorus and metamorphic and igneous systems. So I'm basically put 4 little kind of screen grabs from various papers here. And one thing that I think that we actually lack in terms of our understanding of accessory minerals, what causes them to ultimately grow and recrystallize. And so I've just put a scattering of things here, just showing how I don't think we really understand it too well. And so when we apply equilibrium processes to understand accessory minerals, we have to do so with the realization that equilibrium isn't always attained in the metamorphic system. And especially with things like zircon, where we have zirconium, which can be a quite slow diffusing element in some cases. So I won't dwell on the key facets here, but I'm going to show you briefly each of these plots. This was the one I showed you from Matt Cohn earlier, just showing as the temperature increases, the amount of zirconium in garnet can increase. And we need to consider that when we don't explicitly in these models yet. Do we see evidence for garnet growing and taking in zirconium at different rates and at different concentrations? We absolutely do. Here's an example of a garnet crystal from Daniele Rubato's work showing some zirconium-rich cores and zirconium-poor rims. The thing about accessory mineral modeling in an equilibrium world is we assume everything is nice and equally zoned. There's no zoning. But we see it in the major minerals, and we do see it in accessory minerals too. The top right shows a wonderful study from a couple decades ago, just showing how if we have a reaction that goes between garnet breaking down to cordierite, any of that relic zirconium in there that doesn't want to go into cordierite can just start making little zircon. And so that's another way we can do this. We just break down garnet to produce zircon. It's kind of fun. Here's an example of some experimental work showing how apatite dissolution in an anatectic melt can sometimes produce monazite because of the different diffusivities of calcium and phosphorus. So the calcium goes away really fast and it leaves this kind of overwhelming phosphorus-rich zone around the apatite, which in the right conditions can start to grow monazite. Kind of neat. Again, pointing out that by looking at the real rock record, we can challenge some of the things about the modeling, but also use it to tell us things about what we can try and model next, which is kind of fun. So before I go on to a little bit about trace elements in particular, I just want to emphasize that there's a lot to do in this realm, and it all comes down to comparing what we have from the real world with models and going back and forth and trying to understand processes. So calculations of accessory minerals are tied to experimental solubility expressions, which can be expanded in the future. One of the key kind of things that we need is good experimental petrologists to work on these things. And that is a very, very, I'd say, crucial part of any accessory mineral stuff is doing good experiments. And that is a very challenging thing to do. And so I have so much respect for the experimentalists that try and do these studies and do them because they take so much time, so much effort, and they are invaluable to our community. Integrating of trace element compositions into accessory minerals is not straightforward. We'll talk about that a little bit further. And we need a better understanding of the less understood accessory minerals, allanite, xanthine, and so on. But the key thing, and I've highlighted this here, and this is something that the more and more I do this equilibrium-based modeling and I see divergence from the real world, I ask, is equilibrium the right approach? We are doing phase equilibrium modeling where everything is talking, everything is in equilibrium, but is it? And that's what the modeling can't address. So for the last third, I guess, of this talk, I'll go into accessory minerals and trace elements. And I do consider this the twilight zone because some of us have been trying this, and I think we're just going down these rabbit holes and not really know what to come up with. So before we go into some applications of linking accessory minerals with trace elements, here is just a list of limitations and assumptions. The figures on the right show some experimentally kind of derived kinetic expressions for how we expect zircon, apatite, and monazite to dissolve in a perfect experimental world. And I think the real world gets even more complicated. So we have to understand that when we're doing this modeling, again, there's no kinetic barriers. I alluded to that before. That can't be true. But maybe it's a good enough assumption to start thinking about things. Have we considered all the accessory minerals? No, we haven't. It really depends on the system you're working in. Sometimes zircon's enough, but if you're in a monazite system, you should probably think about what apatite is doing as well. There's no essential structural constituents into major minerals. I've talked about how we can get around that with some modeling, but it's something that we need to consider. We assume all minerals are chemically homogeneous. Not true. Have you ever seen an unzoned zircon? I have not. So be aware of that. When we look at trace elements, we have to think about how they substitute into the minerals. And is this basically a Henrian process? Or in other words, is the concentration tied to activity directly? Or is the integration of a trace element into an accessory mineral actually changing the crystal structure enough where that kind of substitutability is changing? And I think in most cases, we're okay with this assumption, but there are some cases where we're not, such as high thorium monazite. And rock-wide equilibration of major and trace elements, definitely not happening. And the more we do things like laser ablation mapping of silicate minerals, I think the more we'll see that this is true. This is not true. There we go. One thing that three Chris's, Chris, me, Chris Kirkland, and Chris Clark did a little while ago is we started with this question to kind of start the ball rolling of trace elements into accessory minerals, which is zircon, thorium, uranium ratios, which have been reported for decades and used to basically differentiate igneous from metamorphic zircon. And so the underlying assumption here is that thorium-uranium ratio is greater than 1. represent an igneous zircon. If you measure a thorium-uranium ratio of less than 1, it's metamorphic zircon. This is a widely held assumption in the geochemical, petrological, and petrochronological communities. And so what we tried to ask almost 10 years ago now, is that 10 years? Oh man, time flies. Is this assumption robust? And so we tried to model it, okay? So here are 4 plots showing, by integrating basically a thorium and uranium partitioning into major minerals, into melts, and into accessory minerals, what do we get out of that? Essentially, the thorium concentration of the melt, from which the zircon is expected to crystallize, it increases up until the point where monazite is exhausted, and then it decreases. So thorium concentrations of the melt increase, which usually means that thorium in the zircon will increase, but there's some kind of play back and forth with the distribution coefficients and so on. But you can see here, the thorium concentration of zircon is changing a little bit, and then it decreases as we go above that particular threshold. The uranium concentration in zircon decreases quite a bit as we go from low temperature to high temperature. But what comes out of this, the key thing that people look at is not the absolute concentrations, although that's an important thing, I would argue, but people look at the thorium-uranium ratios. So here's an example where we have basically fairly flat up into a value of about 0.1. And then as we increase temperature, that value increases. And then as we increase temperature beyond the monazite outline, where monazite is expected to be completely gone in these models, it kind of stagnates and then eventually decreases a little bit as we go up temperature. So I'll show this in a different series of plots, but the key thing here is that this particular ratio of 0.1 seems to occur both below values and above values in supersolidus metamorphic systems. Now the question you can ask is, does that make it a metamorphic or an igneous zircon? And I don't have an answer to that because that depends on what you define a metamorphic or igneous zircon as. And so here's a different way of portraying some of this. What we have on the right is a mode box diagram before, as again, increasing temperature at a fixed pressure. Amount of garnet's increasing. You can see how the major minerals are changing around as well. You can see the dissolution of monazite, zircon, and apatite. The amount of them goes from basically 100% of them based on what's amount of solidus, decreasing at different rates. The amount of thorium in the monazite is increasing as we go up temperature, which seems to mimic what we see as thorium. As temperatures get higher, natural monazite seems to be higher thorium in general. But finally, the one that everyone kind of wonders about is the thorium-uranium ratio of zircon. And once again, as we increase temperature, we have values in that equilibrated zircon in our system that are predicted to be less than 0.1 and above 0.1. So is it metamorphic igneous zircon? I don't know. Again, it depends on how you define that. But in this single rock, a very simplified geochemical system, we get both values. So is one metamorphic and one igneous? Are both igneous because partial melt is in the rock? Are they both metamorphic because this is mainly a metamorphic process? I don't have an answer to that, but we have values that go on either side of this apparent threshold. We can do the same thing in metabasic rocks. Instead of basically looking at thorium from the context of monazite's a key repository of thorium and what it does kind of impacts what's happening in zircon, we can look at this in terms of what is the main thorium-bearing mineral in metabasic rocks. When present, it seems to be allanite. So here's a little diagram. I'm just going to focus on this one. It's a series of plots that looks about the same. But here we have basically the thorium budget predicted for one of these systems. And when allanite's present, we predict allanite to be the main holder of all the thorium. What that means is that the zircon, any zircon that's growing when allanite's around, is going to have a low thorium-uranium ratio. Once that allanite is gone, we can have a higher thorium-uranium ratio in zircon. So I haven't talked a lot about uranium. Essentially, it's not the key player in this. It seems to be that thorium is the main one and the other thorium-bearing minerals that are around. So that's the implication for metabasic rocks as well. So perhaps it's better to say that zircon with thorium-uranium ratios less than 1 are probably metamorphic, perhaps, and thorium-uranium ratios greater than 1 can be igneous or metamorphic. But again, it depends on how you define these two. And I think that's something that's kind of lost in our community is, well, what's a metamorphic zircon? What's an igneous zircon? How does one define that? Especially when we're at the cusp between metamorphic and igneous processes in high-temperature metamorphic rocks. This is just showing you another study that was done a few years after that on epidote or allanite behavior in metabasites. Again, showing what happens when we have allanite and epidote around. The key thing is that these epidote group minerals are really a key player for thorium. And so if we're thinking about trace elements such as thorium and uranium to a lesser extent, we have to think about the epidote group minerals when we're dealing with metabasic rocks. So one thing that came up fairly recently is some of those model results were compared with those of nanogranitoids. And these are little bits of prograde anatectic melt that are stuck inside of minerals that grow during melting, such as garnet. And so what we have here is the concentrations of thorium in melt based on the modeling that me and the two Chris's did right here. Look pretty high, that's true. And we have those from basically nanogranite studies, which actually show very low thorium concentrations. As kind of a benchmark, there's also the upper continental crust and the lower continental crust. What this is telling us is that there's a big disconnection between measured compositions that are thought to be melt or silicate anatectic melt and that predicted from modeling. And so this is an interesting thing because whenever a model and reality are giving very different results, this is a good thing. It tells us that we're not modeling something appropriately or there's some process we don't understand. And so I was told by Bruna and Omar and even Bernardo, was like, your model results are too high, right? They're right, they are too high. And then I came back at them, right? And I said, well, here's most granites. Your measured nanogranite compositions are too low for what we see in the natural granite record, which is absolutely fascinating. And so I think this is a conversation that I'm going to keep having with Bruna and Omar and Bernardo, which is wonderful, which is the stuff that they have, which I think is the best example we have of primary anatectic melt, are too low compared to the granite record. And the model results we have are too high. So the truth is somewhere in the middle. But why is one giving systematically too low, one giving systematically too high? I don't have an answer. But I think this is wonderful because it's a way to kind of converge our expertise together with different techniques to understand what are the true concentrations of melt in the natural world that yield, say, things like paraluminous granites. So I think this is very fascinating. I'm going to keep bugging them about this, and I just want to see where we can get with this. I'm excited. Here's an example of a bunch of more applications of putting trace elements into basically modeling. Up top is basically some empirical work showing monazite and garnet and how we expect different heavy rare earth elements to be partitioned between them. The top right is zircon and garnet looking at heavy rare earth elements to understand if these two minerals are in equilibrium with each other. Here we have a plot just showing the titania activity as a function of pressure and temperature in a system from which zircon could grow. And here we have some work, and this was Robert Holder's work, showing basically we have different kind of oxidation states of europium in various systems. And how does that impact what we see as europium anomalies in accessory minerals? So I'll have a couple slides just showing a few kind of dig downs into these, but I want to say that there's a lot of opportunity, a lot of things that we can still do. I'm going to skip over this one because I have a finite amount of time to talk to you guys today. But you can go back to the video, and it's basically just showing how we expect the modeling to be integrated with monazite compositions. What I want to get to is basically, I talk too much, I can see that. What I'm trying to get to is basically this one and then the next one. And then I'll probably go into questions shortly thereafter. One thing I think is very important is understanding when we look for temperature proxies, especially with the zircon record, we're looking for temperature. And the key thing for understanding zircon temperature is looking at expressions like this, which have temperature as one of the key variables, but also the activities of silica and titania. And we can model titania activity. And I showed that on the previous slides. But what I try working on right now is there are some anomalously very weird rocks I have from Peru, ultra high temperature rocks. And they have what I expect to be very low titania activities. And these are zircon that have all the other features of ultra high temperature zircon, but their apparent temperatures from titanium and zircon thermometry are like 500 degrees or lower. They just don't sync up. And my speculation about that is that it has to do with very, very low titania activities, which I tried to model with the diagram on the right. But what I'm digging into a little bit deeper is, well, what actually controls titania activities in natural systems? So this is where the modeling is telling us the only way to get this kind of temperature, apparent temperature from a zircon, is very low titania activities, which seem lower than what most rocks should give us. So I'm trying to understand, looking at the oxide minerals, why could this happen? So more on that later. So the one thing that's got most of the attention of kind of the petrological community in the last couple of years, one thing that's becoming looked at in a lot more scrutiny are europium anomalies in zircon and monazite. And what these tell us about, are europium anomalies really reflecting plagioclase? Are they reflecting pressure? Or are they basically being strongly influenced by redox? Because unlike a lot of the other rare earth elements, europium can be divalent or trivalent. And how does this variable redox state actually affect a europium anomaly as we see it in zircon? And so a lot of this work was started again by Robert Holder, who has generously integrated me into a little bit of it. And so I'm going to take it a step further, and this is basically what I like to talk about as kind of a moving picture or model of phase diagrams. So a very brief introduction to these is we have pressure and temperature, we have a metabasite, and here we have plotted on here with contours and kind of appropriate colors is the predicted Europium anomaly in zircon as a function of pressure and temperature. But I'm going to play a video in a second, and it's going to move through a bunch of basically panels showing how these contours will change as a function of what we're going to look at, which is the ferric iron proportion. In other words, we're going to look at very reduced systems where most of the iron is Fe2+. In other words, a lot of the europium is supposed to be 2+ as well. And Fe3+, more oxidized systems, where the europium is expected to be trivalent. And how does this impact the europium anomaly of zircon? So you can look at it in two ways. Here we have basically contours representing the europium anomaly in zircon. You can see they increase as we go up pressure. But also for a single pressure and temperature here, you can track this as the video plays, is I'm going to put on a bunch of little dots on this particular diagram, just as the movie evolves, just showing how we expect the europium anomaly in zircon at that single pressure and single temperature to evolve, as the only thing changing on the right-hand side here will be the amounts of ferric to ferrous iron in our system, which is basically approximating the oxygen fugacity of the system. So I'll play it here. These are fun to watch, right? So the key thing is the contours on the left are changing, and at a fixed pressure, fixed temperature right there, we can see the modeled europium anomaly of zircon is changing a lot. So this doesn't seem to be tied to pressure. It doesn't seem to be tied to plagioclase. What it seems to be tied to in this particular model is just the oxygen fugacity. We can do the same thing with cerium anomalies. So cerium is another one of these rare earth elements where there's two valent states, Ce4+ and Ce3+. And you can see here, as we increase the oxidation or increase the amount of ferric iron in the system, the cerium anomaly increases. So typically cerium anomalies have been tied to, yes, something about oxygen fugacity of the melt from which they crystallize, which is great. We can reproduce that in the modeling. But the europium anomaly is an interesting story because there seems to be a very interesting tie-in to europium anomalies. And just for fun, here's a chondrite normalized rare earth element plot of a zircon for those same sets of models. And again, I'm going to basically play a little movie. It's going to go from very reduced to very oxidized, and we'll see how these various features change at a fixed pressure and a fixed temperature. You can see variable cerium anomalies, variable europium anomalies, and those that are interested, variable heavy rare earth element ratios, indicating that it's not just the amount of garnet. Actually, it actually is. It's just tied to redox of the system. But redox influences the amount of garnet as well. But this little ratio here is not necessarily a proxy directly for pressure. It's a proxy usually for the amount of garnet, which can be influenced by redox. So if I was to say a few things moving forward, accessory minerals and trace element outlook, we have to think about, I've shown you a lot of models, equilibrium processes. Are these applicable to real rocks? Probably not. But when you look at the results of these models, you can start to think about, what are the key drivers? Is it pressure? Is it temperature? Is there something else like redox and oxygen fugacity that can play with these variables? And I think that's very fun and very exciting and allows us to interrogate things that allow us to look at the empirical data sets with new eyes. So I think this modeling that we've been doing, I think they're useful exercises, but they are models and they should be treated as such. Things that kind of spark our imagination and things that allow us to interrogate real data, but don't solve all the problems. So the overall summary of putting this all together, I think geochemical and thermodynamic modeling can be used in many ways. You got to know how to do this, which is basically know the inputs and outputs of your software. But if you know that, anyone can do this. It's not advanced math. It's basic addition, division, subtraction, multiplication. It's just you got to compile a bunch of stuff together into spreadsheets, into code, and do it. And it's really not that hard. And there's lots of us that are happy to guide people when trying this. But I think the bigger question we have to ask before we apply this to real rocks is equilibrium the right approach? But I really encourage people to try this kind of stuff. Try something new. Be creative. It's a great way to explore natural data. So my final thoughts before I wrap up right here is all models are wrong. They're simplifications of the natural world. And we have to keep that in mind. They won't reproduce everything. But when you see a very big divergence from what we observe and what we predict, I think that's a good thing. I think we need to look for those because that tells us we're not modeling something right. And if we're not modeling something right, we don't understand the process well enough to basically reproduce or even get close to the empirical data. So, but these models, when they're treated with care And when considering with appropriate uncertainties, they allow us to test hypotheses of petrological processes. So thank you very much for your attention, everyone. Obrigado for our Brazilian friends. Thanks.
Thank you, Chris. Thank you. It was very interesting. It's very nice to see your models and understand that all models are wrong, but I think they are a very good beginning for our studies. And I will invite the audience to send our questions and comments. Then we're going to read them for Chris. But I have a first question for you, Chris. I don't know if there's a direct answer for this question, but I would like to talk about recrystallized zircon rings. And I want to ask, should we have any different consideration when dealing with recrystallized zircon rings rather than new zircon growth? And I think it's quite difficult to work with this recrystallization. And you were saying about equilibrium. So yeah, if we should consider and how we determine equilibrium. So how we know that the ages and the trace elements acquired on the zircon rings are reliable, or if they are incomplete recrystallization? And when recrystallization it starts in a rock, does it need to have the melt, or it can start before the partial melting? What do you think about this?
Thanks, Katerina. I could talk for 2 hours about that, but I'll try and keep the answers pretty short on this. So I think what we're starting to appreciate in the last few years is there's a lot of dissolution reprecipitation effects on zircon rims, and these can be in subsolidus and supersolidus systems. So when we look at empirical data, sometimes the zircons and the trace elements tell a very comprehensive and fairly tightly constrained story. In other cases, I'd say most cases, there seems to be a lot of spread in the ages or the trace elements, and we have to ask ourselves, is that an analytical artifact, which I won't go into the details of trying to figure that out or not here, or is it real? And if it's real, what is that telling us about the underlying processes? So I think in a lot of the cases it is real. And what we can see in some data sets is there is a decoupling from, even in metamorphic zircon, from the trace elements and the ages, where the ages are consistent, but the trace elements are not, or the other way around. And so how does one evaluate that? Well, you look at a case-for-case basis, and that's where you look at your rock and trying to understand what your questions are. And is it pointing you towards a simple answer or a more complex answer? And you integrate that complexity or simplicity into your tectonic interpretations. But the broader process-based thing we need to do is do a lot more detailed in situ studies on varieties of zircons using the new techniques available to us, nanosims, atom probe. How much are these things varying? Are they doing it predictably so? Do we have clustering of lead? That was one thing the atom probe studies on zircon were looking at that could influence ages. Do we have clustering of other trace elements? And I think I've seen a lot of work from Nathan Dasko and other people as well, looking at dissolution reprecipitation on these rims. I don't think we understand that process well enough. And if we don't understand that process, well, how are we going to interpret trace elements and ages from those rims that we're looking at? So the short answer is, if you have strong evidence for recrystallization, modeling is not going to be your best friend. But what it might tell us is that if you're recrystallizing in an environment where, say, garnet is present and relatively reactive, maybe you'll see a hint of that in the heavy rare earth element signature in your garnet. Maybe it won't be equilibrium, but you might see something related to it. And it also comes down to, for the various components, zirconium versus the trace elements in zircon, for example, how fast are they actually diffusing? And you'll find that the diffusivity rates of the building blocks versus the trace elements might be different. There might be little micro zones of oversaturation around a zircon in a melt that are allowing the zircon to grow, but maybe it's taking a long time for the titanium to get there. And so they're growing without equilibrating with titanium. So there's a lot we could do, but I think if you see obvious recrystallization of zircon rims, and that is what your focus is, you'll want to use the modeling with extra caution. And I wouldn't use sample-specific thermodynamic modeling. Just look at the modeling results and say, what does it generally tell us about things? Hopefully it points you in direction for interpretation, but we can't make our data tighter. If it says a spread, it has a spread, and it's telling us something real.
Yes. So thank you so much, Chris.
Chris, I would also like to thank you for your presentation. It was really interesting for us to put some pieces together. And I was wondering, for the nanorocks you have mentioned, have you compared also with the results of like leucosomes, like in situ leucosome or local leucosomes from these rocks? And what do you think it could happen, like to have such results? You have mentioned now like that titanium is mobilized in a different, let's say, the most appropriate. It's taking longer to go to the zircon. It could be something like this. How you envisage this process?
So what I would say is the issue we have with zircon, for example, is most of the zircon work we do is from separates, right? You crush the rock, you take the zircon out, you analyze them. Because zircon's so hard to see in thin section. Once in a while, though, you'll have just the right rock, and it might be a weird composition, but you have a lot of zircon directly in situ, where you can start to look at these processes and think about what is actually like. So, for example, when a zircon is next to, say, an ilmenite or a magnetite, okay? When you do a little very detailed transect towards that ilmenite, do you see differences in titanium, telling you a various kind of interaction with that neighboring ilmenite? Now, do you see that same thing on the other side of the zircon, where it's next to, say, quartz, which should nominally have very little titanium, or plagioclase or something like that? So I'd say the way we could look at these in the future is more in situ analyses of zircon, which I admit are hard because the zircon are usually very small, and you don't always cut through them with a thin section. But that would start giving us these very detailed things to look at. Now, in leucosomes, what I think are very valuable studies is when you have a migmatite with kind of a melanocratic component and leucocratic component, is look at the zircon from both of those. And some studies that I'm just trying to recollect here is they've shown they actually look kind of similar, and sometimes they look completely different. And I think those are the kind of studies that are very interesting. So what I think would be really cool is if you had one outcrop with various leucosomes, and of course this takes money and time, right? But you try and collect zircon from all those different horizons in the leucosomes, and you ask, are the zircons in each of those leucosomes telling the same story to each other? And then you take the melanocratic components as well. And I've seen this with some monazite studies, and it was all subsolidus, mind you, but you're looking at a layered sequence that looks very similar, a couple meters, but the monazite samples taken from each of those look completely different. But everything else looks like, the rock looks the same composition. So why are the monazites different? The speculation that I think some of us have talked about is maybe there's fluid corridors that we don't see in there. But I'd be curious if the same thing with the leucosomes is when we look at an outcrop scale, rather than just taking like, one sample, like go do a very systematic sampling and see if the zircon in the different areas, including leucosome from slightly different horizons, show the same story or not. I think they won't. And I think it tells us that there's a lot more going on, say, during leucosome crystallization, that's going to be very local to that little pocket. And that little pocket could be a primary melt composition. Very few leucosome actually are. Some of them are more cumulates. And I think those would tell a different story. But I'd love to see that tested empirically.
Yeah, that's really nice. And also, like when you compare like from the paper you have mentioned with Bruna, the composition of the nano granitoids with your granites, with the like the line that you put for reference. And then, do you have the leucosomes from like these rocks that have the garnets with the nanorocks to compare? Are they like in between, or because I wonder, like, is this like some early entrapment that would be still like not so much thorium in the system, like from this all you have mentioned of the breakdown of the phosphorus bearing phases, or I was curious to know if they are like halfway. That's
a good question. I don't know if that data is available, but there's an important point you raised, which is at what point is this garnet trapping this melt? And it's probably fairly early because a lot of the nanogranites are in the core of the garnet, right? So it'd be fairly early in the melting evolution. If it's fairly early in the melt evolution, there's probably lots of monazite still around in the rock that hasn't dissolved. And so just by balance, there's going to be very little thorium in the melt that it could be entrapped by the garnet. So we should ask Bruna and Omar and others. I don't know if that's easily available. So, for example, a lot of the data that they have on nanogranitoids are from basically these kind of plutonic rocks and xenoliths and stuff where you wouldn't actually see a good leucosome. but there may be some with that information that'd be good to compare. And I think that's a very good comparison. But yeah, I think one of the discrepancies that I alluded to is because that's trapping, the nanogranitoids are trapping primary melt fairly early on in the evolution, whereas the granites that have been measured are more of an integration of that goes a bit higher. And the modeling is just over predicting the amount of thorium in melt. And that's simply because I think monazite doesn't dissolve as fast as the modeling predicts. I think there's a kinetic hindrance. That's my guess, which leaves kind of a thorium depleted melt around initially. But once melting goes long enough, then the monazite can break down. That melt can attain a high thorium concentration and go up and make a paraluminous granite. So short answer, I don't know what the leucosomes tell us, but I think there is a petrological explanation why there is a divergence in those kind of 3 data sets.
Thank you, Chris. Really nice to discuss with you.
Thank you, Chris, for your presentation.
We do have some questions. Sorry,
Yeah,
Rafael, go ahead.
So thank you again for your presentation. It was very funny as well. And so I have a prank to you. For several years, geochronologists and petrologists understand zircon age as metamorphic peak of high-grade rocks, And so this is more complex than this. So what we should do with the huge data set that we have that could be misunderstood?
So it comes down to, the metamorphic peak age versus other ages in a metamorphic system. Yeah. And that's interesting because, we usually tie metamorphism in the big databases, maximum T, pressure at that, age. And if you look at, say, the compilations by Mike Brown showing secular change in metamorphism, it's usually at age. Now, it really depends on the resolution of what you're trying to ask. So, for example, some people that work on Precambrian rocks don't want to know if metamorphism was peak at 1875 or 1874. They don't really care. They know it's around 1870, and that's enough. And I think if you look at the timescales of metamorphic processes, let's look at 10 million years, maybe 20, maybe 30, I don't know. But if your question about when metamorphism occurred is just relevant to that kind of time frame, probably you don't have to worry about it. But when you're really starting to dig down into, the intricacies of when did heating start, when did burial start, when did peak start, when did exhumation start, then we need to be a bit more cautious of what is that zircon actually recording. And to Katarina's point earlier, it's, well, is it actually recording an equilibrium process? Is there something else at play? When is it most likely to recrystallize? That would probably be near the peak, I imagine. And so if that's where the age is locking in, great. But that would need to be done on kind of a sample to sample individual scale that makes it challenging. So I guess it comes down to, Raphael, like, what resolution do you want to know that answer to? And if you wanted to know it to like a 1,000,000-year time scale, well, you need very high precision geochronology tied to very good observations. But if you just want to know, broadly speaking, is my peak of metamorphism at 600 or 1,200 million years ago? Yeah. Zircon's fine. Yeah.
Thank you.
Hi, Chris. I have a question for you. Thank you for your nice presentation. Actually, there are 2 questions. The first one is a general thing that I don't understand really well. It's about the oxidation state during a PT path of a metamorphic rock. Do you expect this change a lot from the prograde to peak and retrograde? Or it's something that's inherent to the rock itself? It starts with one oxidation state and then go to the peak, and then, or this depend on the mineral reactions on the path. And the other question is about the, can we model fractional crystallization with accessory minerals in your models, or it's something that is still improving to better understand like what we used to see in these minerals, like zones of growing and different trace element compositions, for example?
Thanks, Lucas. I'll start with the second question because I think the answer is going to be easier. Yeah, yes, one can fractionally crystallize zircon in these systems. You just have to do it iteratively with modeling I've done a little bit myself. It usually doesn't change the story drastically, but it does have subtle implications for things. But that being said, I mean, if we think of simple fractional crystallization, either incremental or continuous, is that the right petrological process for how zircon grows? And if there are little zones of way zircon's growing, then it dissolves a bit, then it grows. And people have thought about this for magma recharge events. Then fractional crystallization is not the right approach because you're actually bringing in new material and so on. So one can do it, absolutely. I've done a little bit of it myself. But I think it comes down to understanding more what processes are naturally occurring and if that would be the right approach for your process. So it can be done, but whether one wants to do it or not, it really depends on what's happening. And a lot of people try to explain like the zoning in zircon, even in igneous zircon. And I don't think there's a good consensus on it. There's lots of discussion on what's causing that. So until we can kind of come up with something testable with the modeling, I'd say we want to be careful with pushing the modeling to solve that problem. I've tried. I don't think we have enough kind of observations or empirical data to really set that out. But I've seen some stuff at conferences, I don't think it's published yet, on explaining some of these zones where part of it has to do with diffusivity and part of it might have to do with a fractional crystallization like process. But we'll see when that comes out. Okay. The first question, which I think is the hardest one to answer, is do we expect oxidation state to change along a pressure temperature evolution? So a lot of people have thought about this, and I think there's diverging opinions. The end members are everything is externally buffered. So in a low temperature metamorphic system, there's some fluid coming through and it's buffering the redox state of that during the process. And the end member on the other side is that you essentially have a fixed amount of ferric to ferrous iron in the rock. That doesn't change across the whole PT evolution. But that being said, that amount to ferrous iron, right, that's going to be going into different minerals along the way as you basically increase temperature, hit your peak, you come down in temperature. And so in that case, various silicate and oxide minerals will be growing or breaking down. And it does impact the chemical activity, the chemical potential of oxygen, which we relate to oxygen activity, which is related to oxygen fugacity, which is related to redox. But essentially the chemical potential of oxygen in these equilibrated systems, right, they will change along a PT evolution. And so what that means is if you look at, say, the delta QFM, FMQ, nickel oxide, whatever buffer you want to use, because all these things do change with temperature, you kind of take that out by looking at it relative to a buffer. You can still see how the oxygen fugacity in a system, a metamorphic system, relative to one of these buffers is expected to change. So whether you think that it's completely internally buffered, which would be that case, or externally buffered, which would be kind of some fluid or melt that's kind of, keeping the effective chemical potential oxygen the same, that's open for discussion. I don't have a strong preference, but I do think we need to consider that the oxide minerals are very important in this game. And as they grow, as they recrystallize, as they break down, they're going to be playing with the chemical potential of oxygen in our system. And that's going to have implications for the general oxygen fugacity of the system. And then one can also think, well, is that happening at a rock-wide scale versus just a micro scale? And one needs to think about, well, how effective can electrons move around and things like that, which is really going beyond what my brain can process these days. But I think, Lucas, there's no easy answer. But I think approximating a closed metamorphic system with respect to ferric iron to ferrous iron is probably the best starting point we have until there's other evidence, sample specific, that say something is coming in and buffering that FO2 for some reason. But it's an interplay between the oxides and the iron-bearing silicates that are changing as the evolution occurs, as we see in natural rocks too. That was probably a convoluted answer, Lucas, so you could follow up with anything that you want. I can't hear Ciro.
Maybe he's having some connectivity issues. In the meanwhile, I thought we can read some comments from the audience. Vinicius Tiepo sent to you, fantastic talk, Chris, thanks. You already answered my question regarding detailed studies of trace element distribution in chronometers, but then he sent a question after that. It was empirical data from oxidizing conditions, like europium and cesium, we think these chronometers map-like data would help a lot, right? Could you comment on that?
Can do. Thanks, Vinicius. So with the oxidizing conditions, europium and cerium, I've seen some studies that have tried to map out europium anomalies, say in zircon, using kind of a grid pattern, and I think it's telling us some stuff. And I actually think there's quite a bit of micro-domainal control on these things. Cerium, I haven't seen that done as well, but I'd be very curious for an in situ, say zircon study. Zircon's the one you're going to see cerium europium in, right? So I would love to see that kind of relative to where you are in terms of the oxide minerals around. I would just be very curious. In terms of one thing I think we want to do, but I don't know if we can, is actually measure europium and cerium speciation in zircon with something like a synchrotron, which I know people have done it, but I don't think they've done it in a systematic grid fashion around zircon, for example, to see how the speciation could change spatially in a zircon. I think I've just seen it like, okay, we got a general sense of europium speciation based on the humps on the Zane spectra or something like that. But in terms of something kind of systematically going across a large enough zircon to do that, I think that would help point us in the direction of what these controls are. So my comment on that, Vinicius, is basically, yes, map-like data would really help. And I think looking at the anomalies themselves is great. You could do that with a laser or something like that. But I think any kind of microsynchrotron work would be especially valuable, especially right now, since we're considering, there's a big debate in the community of zircon europium anomalies. Are they related to pressure, feldspar, crustal thickness, and so on, or mostly oxidation state? I think it's both. But I'd be curious to basically look at mapping out a zircon for europium speciation. And I think the prediction is going to be mostly 3+, because that's what goes in there. But is there resolvable amounts of 2+ that varies throughout a zircon crystal? I don't know. I'd love to see that.
Hello, do you hear me now?
Yes.
Okay, it's great to see you again, Chris. We have a question from Lorena Toledo Queiroz. Thanks, Chris, for the amazing talk. I have a question regarding redox state. Could cerium content in zircon be related to monazite breakdown?
Thanks, Cyril. Thanks, Lorena. Nice to see you. Well, hear from you via Cyril. That's fine. So, could cerium content be related to monazite breakdown? So let's think about cerium for a second. So the main we have cerium 3+ trivalent, and basically we have 4+ cerium. And the reason that zircon has such high cerium anomalies compared to other minerals is that it has a site that can take in that kind of tetravalent 4+ cerium, right? And so we have to think about what are, other than oxygen fugacity, which can control how much cerium 3+ versus 4+, as long as there's an electron donor, which is probably iron, we're probably okay with that. But so other than redox, what are the minerals around that can hold on to tetravalent cerium? And so zircon's the main one. Now monazite normally has a larger proportion of the trivalent cerium, the 3+ that goes into it, basically because it's very similar to lanthanum and we have a lot of cerium-rich monazite. So monazite's going to be playing games with the 3+ cerium, which is going to be the dominant one in any realistic geological system. I don't think it's going to play much of a role for the 4+ cerium because it doesn't easily substitute into monazite as far as I understand. Someone can correct me on that. That's totally fine. I think we need to think about other zirconium-rich minerals that could potentially take in 4+ cerium that I haven't seen a lot of work on. I have a hunch that the iron oxides, those that's like titanomagnetite, might be able to take in an appreciable amount of 4+ cerium. That would be my guess. I am kind of working on that now with some very inconclusive results. But the short answer to your question, Lorena, is I don't think it's predominantly a monazite story. I think it's going to be something else. And I have some ideas about that. Feel free to message me offline if you have any ideas as well. But I think we have to understand the cerium 4+, the tetravalent cerium budget throughout the rock. And I don't think we're there yet. I think for the trivalent cerium, for the rare earth elements, I think we kind of know what's happening. So I don't think it's dominantly a monazite control, but happy to discuss that further.
Now Pedro has some questions. Thanks for the presentation, Chris. Could you guide me on what extent can the mechanical entrainment of peritect minerals during melt extraction produce detectable and interpretable signatures in whole rock granite geochemistry? And it continues. More specifically, are there geochemical fingerprints, for example, in major elements, trace elements, rare earth elements patterns, systematics, or redox-sensitive proxies? And that allow us to distinguish between a true melt composition and a melt modified by variable proportions of entrained peritectic minerals such as garnet, orthopyroxene, or ilmenite.
Thanks, Pedro, and thanks, Katerina, for reading that one. So, Pedro, this is a tough one, and so there's debate in the community about how effective peritectic mineral entrainment is in these systems. When you look at natural migmatites, sometimes you see, that leucosome doesn't have any garnet. Why not? When that was one of the main peritectic minerals. And other times you'll see a disproportionately high proportion of garnet, saying, well, that must have been the peritectic mineral, but most of that melt was squeezed out, so we just have these very garnet-rich horizons. So that's kind of what you see in the field with the migmatite realm. Ilmenite, I imagine, to answer your question on that one, I'm guessing its mode is going to be too small to really influence the granite geochemistry down the line. That's a guess. OPX, I don't think is going to be a key player in most granites because it's usually a lower pressure melting one where we think the bulk of the granites produced are not from that kind of reaction, but there will be niche cases where that's important. I think garnet's the key one. And so how does one determine if garnet is kind of that garnet signature is being resolved in the final granite composition? Well, the work by Gary Stevens on peritectic mineral entrainment looked at the major elements to kind of point in that direction, which is you might not see garnet in the granite finally, but perhaps that garnet was there, it dissolved along the way, and you see remnants of that in basically kind of ghost garnet signatures, which would be kind of constrained in the iron and magnesium composition. But I think the key thing there is when you look at these systems, you have to look at a variety of rocks from that same system to come up with a trend. And there's this kind of a push right now to do more with less. So we analyze 3 granites and we try and tell the story of the world about it, right? But I think to understand your question, which is distinguishing a true melt from that modified by variable peritectic entrainment, I think you need a good set from that basically plutonic complex that shows the evolution. And do any of those evolutionary vectors point back to what could have been garnet? Can they be anchored to garnet one way or another? So I don't know if redox is going to be a key one because there's other things that are buffering the redox in the system beyond just garnet, for example. I don't know if the rare earth elements will tell a story. It really depends on how rare earth element rich the garnet is, how much the garnet is becomes a mass balance thing. But I'd say, I mean, this is just me kind of rehashing what Gary Stevens and crew did back a few decades ago, which is looking at the major elements. But I think the key thing is you need to look at a lot of samples for an individual sample to sample basis. I don't think you can do it on its own. You have to look at kind of the totality of that plutonic system. And in terms of migmatites, if you look at leucosomes, very few of them are going to be primary melt compositions, just because of the dynamics that are happening when these migmatites are forming. You're squishing them, you're squishing melt around. I think Ed Sawyer did some work in the late 1980s that showed, like, of, say, for example, 10 leucosome compositions, maybe 1 or 2 might be close to primary melt. The rest of them are accumulates or, in some cases, residual melt pockets off to the side. So I'd say major elements, lots of samples. That's my very short answer.
Yeah, we have some comments. Thanks, Chris.
So thank you so much, Chris. It was really nice to see your presentation and all discussions. And I'm sure this will have a lot of follow-up when we meet and when people will for sure contact you. I would like to invite also who were watching the presentation and invite everybody to join us in the next PTT Talk next month. And that's it. Thank you so much, everybody.
Thank you. Thank you, Chris.
Thank you, everyone. Obrigado.
Obrigado.
Thank you, Chris. It was amazing.
Thank you, Chris. Nice to see you again.